This is lesson 2 in chapter 20, and we have a weird title, Motional EMF. What do we mean by motional? And we've got that archaic EMF, which stands for electromotive force. And of course, EMF isn't even a force. EMF is an old-fashioned way of talking about voltage. And I often say that EMF is the oomph, the push, the work per charge it takes to move a charge through a circuit. Now, emotional is not what this is about, but motional means there's got to be something that's moving. And when we say that something is moving, we are referring to the fact that you can get some voltage, some oomph, obviously, if you were to hook a wire up to a battery. That voltage is the result of chemistry, having two different metals, one of which wants to lose its electrons more than the other. We talked about that in electrochemistry when we did our that unit in chemistry class. But there are other ways to get or establish a oomph or voltage as well. And that requires there to be motion between magnetic flux lines and a wire. Now you can move the wire in the magnetic field, or you can move the magnet past the wire. Also, your magnet could be an electromagnet created by wires in a solenoid and a charge going through those wires creating a magnetic field. Or your magnet can be a permanent magnet. That's the result of the chemistry of the iron atom and all of the domains aligning, something we talked about in chapter 19. In any case, you've got to have relative motion between the magnetic field, represented by the flux lines, and the wire or wires. So what's got to be moving here is one or the other, or theoretically both. That's where we get the idea of motional from. Now, if we look at the picture in the upper right, you'll notice a bunch of green X's. These green X's represent a magnetic field. Do you remember which way that magnetic field evidently must be going? Hopefully you said into the page, because it looks like the back end of an arrow. We also have a wire represented by the skinny gray rectangle, and that will be our conducting material. And the problem says that we're moving this wire through the flux lines going to the right. In other words, as long as you have motion between the wire and the flux lines, if the wire is breaking through the flux lines, so to speak, you are going to induce a charge, a current, I should say, or a voltage. Now, if this wire is moving towards the right, the picture, it says that your electrons are going to begin to travel down the page in the direction of the blue arrow. And you might ask, is that arbitrary, or can I predict that? Well, let's go back to our right-hand rule. And here's a trick. Your book doesn't talk about this. Your right-hand rule is used for the movement of positive charge, which is the conventional way in which we talk about current. The current leaves the positive post of the battery and comes back plumb tuckered out to the negative post. But here we're focusing for a minute on the electrons. Electrons are a negative charge. So guess what? You're going to use your left-hand rule, which we haven't had before, to find out which direction the electrons will travel. And be ready for this on a test. If you have to use your hand to make a prediction on a test, and you're predicting the motion of an electron, you have to use your left hand. So, take your fingers, which will represent the magnetic field, and you should be doing this right now, and have your hand flat and have your fingers going straight down into the page. Now rotate your wrist so that your thumb is pointing in the direction of the red arrow. As a result, if you've done this right, the palm of your hand is going down the page. It's like the palm of your hand is going to push the electrons to the bottom of the page. And that would be an accurate prediction. In other words, as the electrons begin to get pushed to the bottom of the page, you establish a positive region or charge on the top of the arrow, towards the top of the page. In other words, you've created a potential difference between the positive end and the negative end. So in a regular battery, like a D cell or a AA, where the chemistry establishes the positive and the negative, in this case, the motion of the wire in the electrical magnetic field is what is establishing that potential difference. So when we come down here, you might remember that we have force equals QVB, and that would be the force that is pushing the electrons down the page. Your QE is going to be the electrical force that's going to want to attract the electrons back to the top of the page where the positive charge is. And as a result, these two forces are equal to each other. Notice that the charge cancels out. And so you get this. And then when we come down to the next equation, you can see then that if we multiply both sides of the equation by L, we get this equation right here. In other words, my voltage equals B, the strength of the magnetic field, L, the length of the wire that is in the magnetic field, and V, the velocity with which the wire is moving in the magnetic field. All three of these would cause that potential difference per charge to increase, the voltage to increase. Coming down to the bottom of the page, looking at this picture, we've got something a little different going on here. Imagine that we had a railroad track with two steel beams, and we can make this much smaller. It doesn't have to be as big as a railroad track. But imagine we have two metal rails represented in gray, horizontal, parallel to each other. Imagine we have another metal bar pictured in brown that is making physical contact with the two gray rails. Imagine we have a resistor, just so work is going to be done and we don't have a short circuit, represented by the red zigzag line on the left. And notice that the magnetic field again is going which direction? Into the page. Now, in this particular illustration, we're going to imagine that we're sliding the metal rail, the metal bar in brown, on the two metal rails towards the right. As a result of doing that, the area bounded by the wire with the resistor in it, the two metal rails, and the brown metal bar is going to get bigger and bigger and bigger, meaning it's going to be encompassing more and more and more green X's, more and more and more magnetic flux lines going into the page. And we might want to say, okay, as we're moving that bar towards the right, what is going to happen? You're actually going to get a force, but then you're going to have Lenz's law kick in and induce a current in the wire that's going to go in the opposite direction to counteract that force. And you can use your right hand again, because we're talking about the movement of positive charge. You should be doing this now. Have a flat hand. Have your fingers going straight into the page for the magnetic field. Have your thumb going towards the right for velocity. As a result, the palm of your hand is pointing towards the top of the page, implying that you're going to get a current going clockwise in your loop. But as you do that, in the bar, there's going to be a pushback, a Lenz's law effect. We'll talk a little bit about that later. This is your motional EMF. And if we look at the bottom of the page, let's see if I can get this. There we go. You can see, first of all, that your voltage, and we're down here, your voltage that is being induced, again, is proportional to the strength of the magnetic field. The stronger the magnet, the better or greater the voltage you'll get. You need as much wire as you can get in the magnetic field, L. The faster you move the wire, the better, V. And you might say, well, where did the negative sign go from Lenz's law? Well, you'll notice that your script E for electromotive force has two lines on either side of it, absolute value. We're just talking here about the magnitude of the motional EMF, not necessarily its direction. Now, there is an application for this that could be kind of interesting. And that application is called a railgun. The idea that you can take advantage of this phenomenon and shoot something. And a couple years ago, one of our engineering students on the robotics team actually made a very small little railgun that could shoot a metal bar out of a solenoid. And we have it at school, but you can watch videos on that. I haven't looked for one yet. We can check out some of the math problems. The theory and concept in this chapter is quite technical. The math isn't that bad. For example, in this problem, what is the induced EMF as an airplane is traveling through the magnetic field of the Earth in the air? Interesting problem. You didn't ever thought about the airplane from wingtip to wingtip being like a metal bar, and it's cutting through the flux lines of the Earth's magnetic field as they emanate from the North Pole and curve around in space and go towards the South Pole. Well, what you would need to know is the strength of the Earth's magnetic field, which is 0.6 ten-thousandths of a Tesla. And if the wingtip to wingtip length is 30 meters, and the plane is traveling at 250 meters per second, you actually induce about a half a volt from one tip to the other tip. And of course, it would depend upon which direction your airplane is flying, in terms of whether it's going perpendicularly through the Earth's magnetic field or not. Down here at the bottom, we have, again, the electromotive force equals BLV for this problem about a bar that's sliding along, has a certain length, and it's there's going to be a resistor in the circuit. This goes back to the figure 20.16a that we began this talk with. We can use Ohm's law at the very bottom to find the current. And let me see if I missed anything. Nope. We can find the power or the wattage. You might remember that power equals current times voltage, or it could be calculated I squared times R. We can even calculate the motional force. But now we come to what is perhaps the crux of this chapter in terms of application, and that's the operation of a generator. Now, this particular picture is going to be of a alternating current generator, AC, which means a generator that is constructed like this. Of course, it would be huge. It would be a generator that would it would be greater in size than our entire classroom back at school. But as the wires are moving in the magnetic field, it will create an oscillating current. And the more different magnets you have around an axis, the more peaks and valleys you're going to get. But the current is going to oscillate positive, negative, positive, negative. In North America, our generators operate at 60 times a second. The current oscillates 60 times, reverses direction 60 times each second. And of course, every time you reverse direction, you're expanding and collapsing a magnetic field. And so right off the bat, you don't have to close and open a switch like on a DC circuit. You don't have to physically move a permanent magnet around. You get your magnetic flux lines cutting through wires automatically. In Europe, and I think in South America, they generate their electricity at 50 cycles per second. Another word for a cycle per second is a hertz. That's a little bit more about that in, I think, chapter 21. Now, if you go back to page 635, and you may want to pause for a minute and do this, you'll see a similar looking picture when we talked about how does a motor operate. And here is a key point. A motor is a generator run in reverse. Or we could say a generator is a motor run in reverse. In a motor, what we do is we have a source of electricity pushing a charge through wires in a magnetic field. And when we do that, the wires move. And if we construct it right, the wires can move about an axis spinning. We connect a rotor shaft to that solenoid of wire, and we connect things to that rotor shaft like if we had an electrical engine in a car, we might need to have a differential, but we would be able to make the axle with tires on it go around. In a generator, we do the opposite. In a generator, we provide the motion to wires in a magnetic field, and as a result, we get electricity. We get current in the wire. Because in a generator, we want to generate current, generate electricity. In a motor, you need the electricity to generate motion, a spinning rotator shaft. I hope that made sense. If I was at school, I'd do a demo. I have 2 hand generators where I turn a crank and it generates electricity. But if I hook their wires up to each other, I can turn the handle of one generator myself, and the electricity that is generated will go to the other generator and make its handle turn because it turned the other generator into a motor. And then if you were to go to the other, what was a motor, and this time you were to turn the handle of what was the motor and turn it so it's a generator, then the handle on my generator, which is now a motor, would turn. And so the way this works, and you have to look very carefully here, we have these slip rings, which means they're slipping past the brushes, which enable the wire to the external circuit to conduct the electrical charge without getting all twisted up as the slip rings spin. The slip rings are connected to a solenoid that's going to be turning inside the magnetic field of the permanent magnet. Actually, you have 2 permanent magnets. the North Pole on one, the South Pole on the other. So you can imagine magnetic flux lines going from the North Pole to the South Pole, and as the wires turn, as somebody turns the wires, those wires of the solenoid, it looks like a little rectangle there, will be breaking through the flux lines. Now, the top part of the rectangle representing the solenoid is going to be spinning clockwise, if you're looking at it from the bottom left at an angle, and it's going to come up past the North Pole, curve around the top, and start to go down past the South Pole. Meanwhile, the other side of that loop, which right now looks like it's at the very bottom of the South Pole, part of the magnet, it's going to curve around and begin to go over towards the North Pole and spin up through the flux lines next to the North Pole. And so you have both sides of your loop spinning through the magnetic field, reinforcing each other. And of course, every time the side that is coming up past the North Pole spins around and starts going down to the South Pole, the current's going to get reversed. And as a result, and the same for the other side, and so your current is going to oscillate. Alternating current, AC current, and of course this is the current that you have in the outlets in your house. Batteries, like your car battery and a D cell or a AA, that's all direct current. Now here's some very gigantic electrical generators. And what turns the electrical generator? How do we get these massive solenoids to turn in a magnetic field? You can kind of see the black magnets spaced around by having multiple magnets on opposite sides of each other, as opposed to just two like you saw in the previous diagram. We have multiple sine waves, and it evens out the humps so that all the crests and all the troughs are not on top of each other, because that would be very weird if all electrical devices would surge and stop and surge and stop. It evens out the current, because each sine wave is a little bit farther along than the previous sine wave. In any case, what's turning the wires? Well, we have all kinds of ways to turn these wires. For example, we can have falling water. We can have coal-fired plant producing steam that spins the turbine. We can use wind in a windmill. We can generate steam from a nuclear reaction. These are all ways that we can create the energy to turn wires in a magnetic field, generating electricity. And when we begin to talk about the magnitude of this voltage, down here in equation 20.7, I won't go through the derivation that begins with this equation up here, but in the end, the magnitude of the voltage that you're inducing depends, as you would expect, on the number of turns of wire, which can be in the thousands, capital letter N. It depends upon the strength of the magnetic field, B, and the rest of this depends upon, the A depends upon the cross-sectional area of your loop that's spinning in the magnetic field, and then the rest has to do with the speed at which this coil is rotating in the magnetic field. The bottom of the page reminds you again that we have a torque going on here. And you get your maximum amount of voltage when each side, represented by B to C in picture A, or D to A in picture A, when each side is moving perpendicularly up or down the page, because then you're breaking through the flux lines at a 90-degree angle. But once you reach kind of the top where the picture shows it, once your length from point B to point C starts to move parallel with the green flux lines, then your induced voltage goes to zero. Fortunately, the momentum of your spinning solenoid carries it past so it can begin to go down the other side and you continue to induce voltage. Now, if we wanted to create a direct current generator instead of a alternating current generator, DC instead of AC, we need those split rings in the commutator like we had way back with the motor in the previous chapter. And so what the split ring does is as soon as your section of your solenoid that's cutting up through the north pole side of the magnet begins to coast over and gets ready to go down to the south side, thus changing the direction of the current, mechanically it actually switches to the other split ring as opposed to the one that it was brushing against previously, and that keeps the current going in the same direction. So you reverse the reversal and you get direct current. And again, the math here is not all that difficult. You just have to keep the formulas straight. Again, also remember that when we talk about the velocity of something is spinning, we have to convert any revolutions per minute, which is typically how we talk about things that are spinning in everyday language, and convert it into radians per second. Now, there is a price to pay. There is a pushback. Lenz's law has to be heard from. And the idea here is that every time you begin to have current going through a wire, you've induced a voltage that begins to generate current. The current starts to go through the wire. It's going to move out from the positive post of your generator. It's going to do work on your resistor, in this case a 10 ohm coil, but this could be anything like a light bulb or an electric motor or some appliance. But as soon as you have electricity going through wire, the moving charge going through the wire is going to create its own magnetic field. And that its own magnetic field that it creates, it's going to be going around the wire, is actually going to push back and induce a bit of current opposing the movement of the current that's going through it in the first place. We call that a back EMF. It's a little bit of voltage that's reminding you it costs. It's going to cancel out a little bit of your voltage. That's called the back EMF. And it's a little easier to understand this if we get into the topic of self-inductance in just a few minutes. In other words, when current goes through a wire, that current creates its own magnetic field. And again, if you look at the picture, 20.24, and take out your right hand, and if you have your thumb of your right hand going in the direction of the current represented by the purple arrow, and I'm doing the one at the top of the picture, you'll notice that the natural curvature of your fingers is the same as the curvature of the green arrows going about the wire. So you're inducing a magnetic field as a result of the current going through the wire. Now, the self-inductance here isn't going to be much because you just have a single wire. But if you were to have a whole solenoid, if you were to have a whole bunch of turns of wire so that there's lots of wire right next to more wire, the induced magnetic field or magnetic field that you're creating is going to affect the nearby wires. This is what we mean by self-inductance and a self-induced EMF. And again, if you come down here to the equation at the bottom of the page, you'll notice that, as you might expect, This self-inductance is going to depend upon the number of turns of wire. The more, the greater. The self-inductance is going to depend upon how rapidly that current is surging or reversing direction or changing in magnitude. That's your delta phi over delta t. And then you got the negative sign saying it's going to be a pushback. It's going to be a back EMF. It's going to oppose what's creating the magnetic field in the first place. So, to give a bit of a practical application here, in this picture, we have a whole solenoid, and there's a metal bar through it. In an electrical device, this is called an inductor. If this was part of a broader circuit, it's an inductor. And so far in circuits, we've had resistors and capacitors, and now we have inductors that we can put in a circuit. And every one of them has a function. Every one of them accomplishes a purpose for us. Years ago when I was in high school and I had my own little transistor radio, of course I took it apart, which wasn't the best thing for the radio, and I could see the capacitors, and I could see the transistors and the resistors, and I could also see these little inductors, which were little teeny tiny solenoids, and almost always they had a metal bar going through them to enhance the effect. And so if you take your right hand in picture A, and you got your fingers in this case following the direction of the current over on the right side of the bar, of where the solenoid is going over the bar, and then be underneath it's coming back around, and the coil winds to the left, and you've got 3 coils, and then it comes out the bottom on the left side. You'll notice that your thumb, as your fingers curl over the bar, your thumb is going to be pointing towards the north. So that means you have an electromagnet. This inductor is, in this case, isolated from the rest of the circuit, is just an electromagnet with the north pole to the left. Now, if the current were to surge, increase, or if the current were to decrease, if the current were to change direction with an alternating generator, if the current were to increase or decrease because you're turning an electrical switch to a battery on or off, in any case, as the current increases or decreases, it's going to create a magnetic field in the wire, and especially where the wires are in close proximity, which is the solenoid, each wire's magnetic field is going to affect the nearby wires. So even though each wire is creating its own magnetic field as the current goes through it, and this is a magnetic field that is different from the electromagnet that I described in part A, each wire will experience the magnetic field being induced by the adjacent wires. And that magnetic field, by Lenz's law, is going to oppose the very current that would created the original electromagnet in the first place. We call this the self-inductance. And the self-inductance depends upon, and you can see in equation 20.9, the self-inductance is, and my marker's not working. That's not what I wanted. The self-inductance depends upon how rapidly that current is changing, because it's the current that's going to induce a magnetic field on every centimeter of that wire, and it's going to be most pronounced when the wires are close together, because each part of the wire will experience the changing magnetic field by the surrounding wires, because the current is changing, delta I over delta T. And again, why is the current changing? Because if you have a battery, you might be turning the switch on and off. So the current is going to its max, going to zero, going to max, going to zero. Or if it's an alternating current source, then your current is changing direction 60 times a second. Max, min, max, min. In any case, that's why you have the delta I, delta T being proportional to the voltage. Also, notice that the letter L stands for the inductance of the inductor. Now, the L would be a function of the mechanical properties and dimensions and size and materials of the actual inductor itself. And usually we can look up the inductance for a given inductor. And there's the negative sign due to Lenz's law. The reason I said Henry's law is because Henry is the unit that we use for inductance. The unit of inductance is the Henry. So every inductor in an electronic device will have a ranking of Henrys, just like a resistor is ranked in ohms, and just like a capacitor would be ranked in capacitance. And the Henry is named for Joseph Henry. He's one of the very first American physicists after Benjamin Franklin to become really famous, and also to kind of establish the United States as being just as reputable in the field of science as all your European countries were. He was from Eastern New York, and the reason I say that is because my mom was from Eastern New York, where Albany is. My mom grew up in a nearby town called Amsterdam, and I can remember when we'd visit there, lots of things were named Henry. Finally, when we talk about a solenoid and electricity going through that solenoid and inducing an EMF, measuring the inductance of that solenoid, and recognizing that there's going to be a bit of a price to pay because each stretch of wire is going to be creating a magnetic field as the current changes in it that will affect the surrounding wire. We can measure that inductance in equation 20.11. And this shows you how L, the proportional constant that represents the mechanical properties of the inductor itself, is going to depend upon the number of turns of wire squared, the permittivity of free space, mu. Remember, permittivity of free space is the ability of space or air or whatever the environment might be to hold a magnetic field, so to speak. It's going to depend upon the dimensions of that solenoid, cross-sectional area A, and the length of the wire. In the next talk, which will be rather brief, we will talk about circuits that have both a resistor and an inductor in it.